We can also do applications of the divergence theorem to some examples that don't immediately look like they apply. So for example, here's a vector field. F of x, y, z is x comma 1 comma z. And we might ask to calculate the integral of the vector field through the 5 sides of the cube that are 0 less than or equal to x less than or equal to 3, 0 less than or equal to y less than or equal to 3, 0 less than or equal to z less than or equal to 3 that are on the bottom. So that's this side and this side and this side and this side, and then there's also a side on the bottom. If we want to do that just by blunt force doing it, that would be 5 surface integrals to calculate, which we could do. The vector field's not that complicated and these surfaces are not so hard to parameterize, but it would take a fair amount of work. Also, we can't immediately use the divergence theorem because these 5 together are not the boundary of a 3-dimensional region. They don't close up. There's kind of an open part on top where there's an edge. And so it doesn't completely surround a 3-dimensional region. But what we can do instead is saying, well, if I want to know the total flow out through these 5 sides, I can instead calculate the total flow out of the whole cube using the divergence theorem, and then subtract away the amount that was flowing through the top of the cube. And that leaves me with the total flow out through the remaining 5 sides. That's the trick you can do. It lets you convert a surface integral over this hideous region to a surface integral over one region. And this technique is very, very handy. So in this case, we can calculate the divergence of f. It's the divergence of the vector field 1 comma x comma 1 comma z. The divergence in this case is 2. The double integral is the integral of 2 with respect to volume. It's going to give us twice the volume of the cube. The cube has sides 3, 3, and 3, and so this volume is 54. That's the total flow outward through the cube. Let's calculate the flow through the top side now. To total flow out of the top of the box, we just have to calculate the surface integral. We parameterize our surface. We know that that's the set of points where z is equal to 3. We know that x and y go between 0 and 3 for this particular box. We calculate our tangent vectors. Tu is 1, 0, 0, and tv is 0, 1, 0, and we calculate their cross product. Then we calculate the double integral of f of phi crossed with that, so that's u1, 3 dotted with 0, 0, 1, and that becomes a double integral of 3 du dv over this. The total is going to be 27 if you go through the steps of calculating this. And so I've done this a little bit quickly, but it calculates that the total flow out of the top is 27, and so the total flow out of the whole thing is 54, so the remaining 5 sides have a total flow of 27 as well.